So the talk today is entitled From Particle Dynamics in Magnetic Field to Building Stationary Solutions of the Maxwell-Vlasov Equation. So this is joint work that has been started a long time ago during the PhD thesis of Benjamin Cambon, which is here. And then I have some collaborators, Michel Vittor, Rémi Dumont, Diego del Castillo Negrete, Guillaume Di Fradaye, and Xavier Garbet. But I would like also to give my thanks to Sean Ogawa, which was a postdoc in my lab, then Elias Laribi, who was a master student under my supervision, and big thanks also to Aurélien Cordonnier, who is doing his PhD currently with me on this topic. So let me first do the presentation. I will start briefly with the scope of the problem, like with what is the problems of fusion, how we can control fusion using magnetic fields, and then I will go to the Hamiltonian approach, how we can use a Hamiltonian to approach the problem, and then discuss some specific case of the problem of creation of transport barriers, and then finally I will add up with a self-consistent solution. So let's start with the scope of the problem. So what we want to do is to realize fusion. So to realize fusion, the reaction that has been chosen is to fuse like a deuterium and a tritium nucleus into a helium, and that releases a helium nucleus and a neutron plus some energy. So typically the alpha particles they keep about 3.5 mega electron volt, while the neutrons they take the lion's share of the energy release. So what is nice about this reaction is the easiest one to reach. I mean, the cross section, like the maximal reaction rate, occurs around 100 keV, which is about 1 billion. If you want to translate it into temperature, it's 1 billion degree. So, why does it need to be so hot? It's because like we need a very hot plasma in order to overcome the Coulomb barrier, the repulsion between the nuclei. So first, how to confine such hot plasmas? So one of the idea is to confine using a magnetic field. So when we have a magnetic field like that, like here, this is a cartoon with a uniform magnetic field, a charged particle is trapped in the sense that it just winds around a magnetic field line. The problem is like, okay, so how to realize such a magnetic field is not very complicated. We just take a coil, and then we have a magnetic field. The problem is like we have particles, yes, they're confined in 2D, like so on a transversal direction, but in a longitudinal direction of the coil, there's no confinement. So what is the idea? But the idea is simply to make it into a torus. We'll just break the coil, and so like that, we hope like the particle will just wind around. Unfortunately, because of the torus configuration, there is a gradient of the magnetic field, and this gradient leads to some drift in the direction, so the z direction, it is usually called. So like, depending on the sign of the particle, the sign of the charge of the particle, but there will be an upward or downward drift, and so the particles are not well confined in this setting. So how to prevent this? This is like mostly the idea of the Tokamak, is to wind, or the stellarator also, is to create a winding magnetic field. So like a small component, which has a toroidal component of the magnetic field that will bring particle down. So the particle, for example, will always be moving up, but because it follows the magnetic field, at one point it will be down again, and so it will be moving up, and it will go back towards the center. So in that sense, like the average time it will spend inside the Tokamak will be much larger. So that's the idea that how people are confined. Another important things like what are the conditions that want to be reached. So I already talked about the reaction. So what is hoped is to reach not 100 keV, but to just reach temperatures that are around 10 keV, so like about 100 million degrees. And then like the tail of the distribution was there will be some particles that will be around 100 keV. And anyway, before that, because it's a cross section, there will be already fusion reactions, and that should be enough to trigger like a controlled mechanism. So the typical densities of the particle is about 10 to the power 20 per cubic meters. So those are more or less are the conditions that we hope to have. And the magnetic field is of the order of the Tesla, a few Teslas. That's in the ITER configuration. So what is the idea is to, as I said, to create this poloidal magnetic field to stabilize the particles. But how to create it? So like in the idea of the tokamak is to use the plasma to create a current inside the plasma that will generate this poloidal magnetic field. So this, in that sense, like the plasma is self-stabilized because of the current, it stays confined. And at the same time, what is nice is like there is ohmic heating. There's still like some ohmic heating. So this heats the plasma because of the current. There will be ohmic and there's a resistivity of the plasma. So at the same time, it stabilizes the plasma and it heats it up. The only problem is like the resistivity decreases extremely fast with temperature. And actually, this system works up to about 1 keV to heat up the plasma. So there's still one order of magnitude to reach 10 keV in order to reach the fusion condition. So additional heating is necessary. So I'm giving you some of the scales, the typical scales that you can reach. So like you have the, for example, the cyclotron electronic frequency is about 100 gigahertz. I want to say like in order like for a fusion reactor to be functioning, we need to stabilize the plasma for about a minute. So you have an idea of the order of magnitudes. Like the same, like for the lengths, the typical radius, the Larmor radius of the electron is about 0.1 millimeter, 0.1 millimeter, while the typical radius of the devices is about, the order is a meter. And then like the typical mean free pass is about 1 kilometer. So what we can see is like, so when mean free pass in a sense like between different collisions, in between quotes, so there is a very huge also scales, large amount of scales in the space and in speeds, like when we compute the speed of the electron. So we are happy because the typical speed is about c over 10. So like we are non-relativistic in that sense, but still like this means like near close to the border, like close to the boundaries of the plasma, where like there's matter, like here, like the plasma has to be much colder. So like the range of scales in speeds has to be also very, very wide. So what are the, but given what we saw, like we are above 1 keV, so there is almost no resistivity. And so we end up with something which we called a collisionless non-relativistic plasma. And in this setting, what is well best suited to describe the plasma is a Vlasov equation coupled to Maxwell equations. So the Vlasov, because there is no collisions, so we switch from Boltzmann to Vlasov equation. And what is nice is like here in this setting, like the particle trajectories, thus they can be tackled using classical conservative mechanics. Because we are far from any quantum effect also, we are non-relativistic. And so let's go to the Hamiltonian approach. So what are the Hamiltonian approaches in this setting? So first, I'm going to talk about the charged particle that is evolving in a magnetic field and also in an electric field. So we can write it simply like it has a natural Hamiltonian, which can be written this way, where A is the vector potential and V is just the electric potential. So this is one Hamiltonian to describe the particle, the motions of the particles. Then there is another Hamiltonian. It's like actually like everybody knows that the magnetic field is a divergence-free field, and in fact, when you have a three-dimensional field that is divergence-free, well, any field, but when it's 3D, it's more interesting. You can transform this into a Hamiltonian system. When you're looking at the field lines, you can transform this into a Hamiltonian system with 1.5 degree of freedom. So it will be time dependent and generically chaotic. So unless you have a symmetry in the system that destroys one, creates one invariant, then you will have integrable field lines. But if you don't have any symmetry that gives you these conditions, you end up with a chaotic field lines in the system. And then the last, which I will not talk too much about, the Hamiltonian form, is like actually the Vlasov-Maxwell equations can be tackled using also a Hamiltonian formalism, but that is more general with like Lie Poisson bracket and special form of packets that can deal with, and then the observables of the system, or the dynamical equations of the system, are the one particle density function F and the magnetic and electric field. So I will not go to this, but I just want to remind you, like, what is the Vlasov equation? It just means that we are conserving the probability along in the phase space. So we just write like some kind of a bit like a hydrodynamic equation of conservation in a phase space, and that translates into like this kind of equation where F is the force that is uh, felt by the particles, V is the speed of the particles, and it's a function itself. So what this could be nice, but the problem like is, well, analytically it's very difficult to solve, unless the cases are trivial. Maybe the ones that we'll talk about later are a bit trivial in that sense. But for numerical simulation, this is also very hard, because first there is a very wide range of scales. Like we see, like time scales, they range from 10 to the minus 11 to a minute, so like 10 or 60. So like so it's a huge range, like 12 orders of magnitude in time. Um, the idea. So one of the idea, and I talk about the other problems also. So one of the ideas was to use an adiabatic invariant. In fact, like there is the magnetic moment, which can be considered like as a adiabatic invariant in special settings where like the magnetic field is changing smoothly with time, and like there is also some properties of dynamics that have to like a pitch angle, not small, so things like that. And so like if you assume this is invariant, so it becomes a constant, then you can try to make a change of variables, and then you end up with what is called gyrokinetics. So because when you make the change of variables, you are removing 1 degree of freedom. So there is like, because this adiabatic moment is like about the flux of the magnetic field on the circle, but is the projection of the trajectory on the perpendicular magnetic field line. So if this is a constant, the associated angle that uh, we kind of ignore, and so we are left with actually a system with a 4-dimension instead of using 6-dimension. So this is important, like it reduces dimensionality. So 4-dimension plus 1 dimension, which is those constants, those mu zeros for each particles in some ways, the distribution of these constants that doesn't change. And also what is nice is when you ignore this fast rotation, you can change, instead of going to the few gigahertz, you can go to the megahertz scale. So you gain like 3-4 orders of magnitude in time. So when you want to perform a simulation, you have much more, it becomes feasible actually with current computing powers. So those codes, those gyrokinetic codes, that have reached in the last 10 years about industrial level, meaning like they're running everywhere and people are running them, trying to analyze the results of these codes. So one of the things that we can ask ourselves is like, does this make sense? Can we do this? So what we'll do is like we will consider just a simple Hamiltonian approach, like of like trying to follow a particle in a magnetic field, and we'll ignore the presence. Sorry for there was like some in the street, like there is. I'm waiting. Okay, so I will talk about this. Just I will ignore any electric field. So here P and Q are the canonically conjugated variables. A is the vector potential. And in order to simplify things, we choose like to fix it in a Coulomb gauge. And so like the divergence of A will be 0. So the coordinate system is like the torus. So we have a magnetic field of the form like which is of this type. Actually, we can see that there is the E phi part is just like the regular part that you will get from just the coil that is the toroidal coil. But then there is this G of R E theta. This is the poloidal component that is generated by the plasma. Okay, so then if you have this kind of, as you can see, like here, like there's a symmetry of a rotation on the angle phi, like around the center, the axis that is the center of the tokamak. So there is a symmetry, and the vector potential that comes from this can be written in this way. So this is the system we want to look. So we have one symmetry. So we have one constant of the motion that is associated to the symmetry, so some kind of angular momentum in some ways, and we have the energy that is fixed. So we have two constants of the motion, but we are in a 3 degrees of freedom system. So if we think of Arnold Liouville, a priori the system is not integrable, and we should have chaos, unless there is a third invariant, which is the magnetic moment. If this is a constant of the motion, then we should fall back to integrable motion. So let us look about that, and we'll see how we tackle this problem. So as I mentioned, the invariant of the motions, sorry, I anticipated, so there's an angular momentum. So actually what we will do first is I will consider the limit of r going to infinity. So in that sense, like r is the radius of the torus, of the donut. So I will keep the small radius constant, but then the radius of the donut will go very, very, very large. So in this limit, like actually the torus becomes a cylinder, and E phi becomes a constant vector, and we are ending up with a cylinder. And so the magnetic field becomes just like some kind of uniform magnetic field. We are in the solenoid, in the cylinder again, and there is still a toroidal, it's not a poloidal component that is, we choose to notation F of R. So in this setting, like analytically, what we show is like actually in this setting, like the motion of particle is integrable, because now we have another degree of freedom. We used to have the rotation along phi, which became a translation along the cylinder, but now because we have a cylinder, we have a second momentum that is preserved, this rotation on the poloidal direction, and so we have a third constant of the motion that makes the motion integrable. And actually, the effective Hamiltonian of a particle can be written in this way. This is just a radial component, and because of the constants of the motion, Pz is a constant and K is some other constant of the motion that is related. So we have an effective Hamiltonian of this form, and actually we can tune F of R, which is related to the poloidal component of the magnetic field in the plasma, and we can tune it in order to create a separatrix. So we can have a system where there is a simple like an unstable fixed point that has a separatrix around it, and so like we have two stable fixed points and one unstable fixed point. And so what we can ask ourselves, like in this setting, like when we go back to the torus with this kind of a magnetic field and this F of R, what will happen near this point, unstable point? And what we see is like there is the classical breaking of the separatrix. And here, like I show about 3 different cases. Like, so the yellow case is for like a aspect ratio between the small radius and the large one of 10,000. Then R equal 1,000, R equal 100. And then we can see like actually the chaotic zone increases. There is still regular trajectories. So in that region, there should still be a third invariant of the motion. There is regularity, but in this area, there is chaos. So the magnetic moment cannot be a constant of the motion in this region. And then it becomes a problem because there are regions where like it doesn't exist. So when you are trying to make a change of variables in the global sense, it can create problems. I show here like mu like for the integrable motion, but already like when we have this very tiny, sorry, I'll go back, tiny separatrix, like here, like I take particles in this yellow region for this, we can see that we have fluctuation of the mu0, the first order, that are about 50%. And when we reach like the typical, what we expect in the Tokamak's ratio, that we have fluctuation of mu, which are like near close to 50, 60%. So it's not a constant anymore, and it's a problem. So let's talk now about also another aspect of fusion, which is like the problem of transport barrier. So usually, in order to tackle those, so how will we approach? Is like I will consider now because typically like one of the ideas to use the magnetic field to create those transport barriers, and most of the studies are made using a cylindrical magnetic field. So here, like we will go back to the cylindrical geometry, that this R goes to infinity limit, but we will perturb the magnetic field. So we'll add a perturbation. So we'll have the generic component that we used to have, plus we will add some modes, some perturbation modes. So If we just add one mode of perturbation, like just it should be like just a pendulum. So like the field lines will still be integrable. But if we add two modes of perturbation, the field lines they should become chaotic. But at the same time, like when we are adding just one mode, and so like the field lines they become just a pendulum, we are destroying the symmetry, the angular symmetry. We are destroying one symmetry. We are just retaining only one symmetry, helical symmetry in some way. And so we have only two constants of the motion, so we should have chaos. So let us see if this is true for the particles. Oh, first, yes, and maybe I'm going to say like it's like we tune F in order to have a non-monotonous Q profile, which is more prone to create transport barrier. So here we follow the recipe that was done in the previous papers. And so what we find is like using these recipes, we have like an effective potential that can have a double well. So we can have a separatrix. And so what happens when we are perturbing this? This is the zero mode. So now we are adding like one perturbation mode. This is the separatrix when there is no perturbation. And when we add one mode, so like the field lines are still integrable, but we have chaos in this region. So like again here in this setting, there is no third invariant, and mu, the invariant, the adiabatic motion is not an adiabatic invariant in this region. So, but also what we could ask ourselves, what happens with the magnetic field line when we are adding perturbations? So like as I saw, like first, like there is one mode that's more or less, so it's integrable, but when we add the second mode, there is suddenly chaos of field lines, and we can see that there is still regular regions, but then there is chaotic region. But then what happens for the particles in this setting? But in fact, what we see is like, depending on the particles, but you can have particles that have regular motion or chaotic motion, as we discussed already with one mode. And when you are adding a second perturbation, actually you can see that it can regularize the particle motion. You can see like here, like that suddenly there is, if we increase a bit the energy and adding a second mode, we can have like a barrier. There is a regular toroid that appears that is blocking from like the low, here this is more or less proportional to the radius, so to the center of the tokamak with the exterior, there is this barrier that protects it. So particles cannot cross, so create some kind of transport barrier. Even though the field lines in this setting were much more chaotic. So there is no direct relation between the motion of the particles and the chaoticity of the field lines, and vice versa. So this is like some kind of cartoon that resonates a bit. I will skip this. What we found on transport barrier. I want to go back now to what we can do. It's like when we have an integrable case, integrable Hamiltonian like that, I will forget about the perturbations. It's very easy actually to find a stationary distribution function. Actually, any function f of 0 of p of q that commutes with the effective Hamiltonian will be a constant of the motion. Well, it will be a stationary distribution of the system. So actually, we have plenty, an infinite number of stationary distribution that we can plug from this study. So which one to choose? So what we did is like we decided to choose the one that maximizes the entropy. The classical, we don't know about it. We don't have a lot of information, so we use information theory, and we say, okay, we will maximize the entropy. So we will try to maximize this entropy, but we have some constraints. We will keep the total number of particles, we will keep the energy constant, and also because we have two invariants in this setting, we have one momentum and two second momentum that are globally conserved. So we have four constraints, and using this maximization, we find that the distribution has to be of this form. And then what, depending on the condition, for example, when we add some kind of plasma rotation, at least like when gamma z is not zero and gamma theta are not zero, what we can notice, like first we can create separatrices in the plasma for the particle dynamics. And close to those separatrix, when we look at the density profile that we can compute analytically, that we can see that there is a very, very steep profile. So actually, what is nice is like we see that the influence of those parameters and those separatrices can be very, very strong and important by creating transport. And but at the same time, what we show is that near those separatrices, we have an unstable fixed point, And in this region, typically there will be some perturbation. So in this region, like the adiabatic moment is not a constant of the motion. So we are not sure that those behavior will be well captured by a gyrokinetic code. I think there will be a problem there. So finally, to conclude my talk, I just want to talk about the self-consistent solution. In this problem before, here, like I just found this thing, but I had external magnetic field was fixed. So how to go beyond? Actually, since we computed here the density, we can also compute the plasma current of those solutions with a stationary distribution. So we can find a plasma current. And then if we want to be self-consistent, what we do is like we just say, okay, the current is generated by the magnetic field using like a Maxwell Ampere law. And then using that law, we find that we end up with a self-consistent equation for the vector potential that can be written in this form. So here we just took into account just the Jz and the current along the cylinder. So if we are doing like this, we can make some analysis. We can dimensionalize the problem, and we find that the exact analytical solution exists when A equals 0, but then they are not physical. At least they don't correspond to solutions that make sense in magnetic fusion context. But maybe it could be interesting near R equals 0. And what we can see is that we expect that near J0, because near the center of the part level, we can expect that to have a parameter that is important. In fact, when A is not 0, we have to resort to a numerical simulation to solve the problem. And as I said, like magnetic profile can lead to region with separatrices, but this parameter is governed by the sign of J0. Actually, when there is only one direction that is self-consistent, we cannot find this J0 to change sign, actually. But also, no, before I continue, is like when we are just using one thing, we can add two species, so like the electrons and the ions, and we can do the same kind of procedures. They could have different temperature, but in the end, to be self-consistent, we end up with the same kind of problem, and just one the equation that is just a bit different. But also what we can do is like also take into account the current on the toroidal direction. And when we do this, we can also again consider either a neutral background or like two species background. It ends up with the same kind of result that we had before. But now we have a two coupled nonlinear PDEs. And what we notice is that here, like in this setting, like we can identify a bifurcation, and J0 can change, the second derivative of the current can change sign, and we have a bifurcation. And actually, when we are going through that bifurcation, I see like when the sign of J second changes sign. I don't know if it's visible here, but we start to have a bump that emerges, and actually more particles are confined. Maybe there is, yes, there's a small hole that appears because the bump is a bit not on the center of the Tokamak, but more particles are confined, and then the profile becomes steeper. So when we increase, so we identify this bifurcation. So this is where I want to conclude. So as I said, gyrokinetic roads, they can give wrong results, especially when we consider transport, because near transport barriers, it could be a problem. So we have to make some tests of stabilities of the obtained analytical density profile that we got. And we would like to compare this with the magnetic dynamic results, and also maybe test other type of solutions, like Linden-Bell approach. And one question that is important: is this useful for a reactor design? So sorry about the noise. So last but not least, I just want to mention that also that this is an online conference because we had the COVID problem, but actually the real live conference that was supposed to occur last May in Marseille will be still going on in next May, end of May in Marseille. So far, we have a clearance so far. So maybe unless the health condition will change a lot, but we are hopeful that it should be going on. So all the people that are already signed up and have an accepted talk, nothing will change. But if other people want to apply or submit an abstract, you are welcome to do it, and we'll consider all new submissions because the website is still open. So I'm giving you here like some slides of Marseille for those that don't know it. This is a beach that is very close to the conference place. And here, like this is where we should have the conference, at least where we used to have it, and I hope we will still be able to do it there. And so here, yes, you have the website of the conference, which is NSC-CCT20. So it's a joint conference between nonlinear science and complexity, and chaos, complexity, and transport. Okay, and so thank you very much.